My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Design and Analysis of Algorithms as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 5 first important short question is: what is the difference between P, NP, NP complete and NP hard problems? Difference between P, NP, NP complete and NP hard problems. P problems. Problems that can be solved quickly in polynomial time by a computer. Example: sorting numbers or finding the shortest path using Dijkstra's algorithm. NP problems. Problems that are hard to solve quickly, but if someone gives you a solution, you can verify it quickly. Example: Sudoku. Checking a failed Sudoku is easy, solving it is hard. NP complete problems. These are the hardest problems in NP. If you find a fast solution for one NP complete problem, you can solve all NP problems quickly. Example: traveling salesperson problem, TSP. NP hard problems. At least as hard as NP complete problems, but may not be verifiable quickly. They are even tougher. Example: halting problem. Quick trick to remember. P is equal to easy to solve. NP is equal to hard to solve, easy to check. NP complete is equal to hardest of NP dot. NP hard is equal to even harder. Next important short question is: to define polynomial time reduction. Why is it used? Polynomial time reduction. Definition: polynomial time reduction is a method of converting one problem into another in polynomial time fast enough to be practical. If we can change problem A into problem B quickly, solving B also solves A. Why it's used? To prove problem difficulty, if a known hard problem can be reduced to another, the second problem is also hard. To classify NP complete problems. Many NP complete problems are proven by reducing one NP complete problem to another. To reuse algorithms, if problem B has a solution, we can solve problem A by first reducing it to B. Example: if we reduce the 3 SAT problem, known NP complete, to the graph coloring problem in polynomial time, solving graph coloring would solve 3 SAT too. Quick memory tip. Think of it like translating a question into another language quickly. If you can solve the translated version, you've solved the original. Next important short question is: 3. Give 2 real-life examples of NP hard problems. Real-life examples of NP hard problems. 1. Traveling salesperson problem, TSP. A salesperson must visit N cities exactly once and return home while minimizing travel distance. In real life, delivery companies like Amazon or courier services face this challenge to find the shortest delivery route. There's no quick formula for large N, solving it perfectly takes a lot of time. Companies use approximation algorithms for faster, near-optimal routes. 2. Job scheduling problem. A company has multiple machines and jobs. The goal is to assign jobs to machines so that the total completion time is minimal. Used in factories, cloud computing, and airlines to optimize schedules. As jobs and machines increase, solving it becomes extremely complex. Quick trick to remember. NP hard problems are like super tough puzzles in daily life. Example: best routes, best schedules. We use smart tricks or approximation because solving them exactly is too slow. Next important short question is: 4. What is NP hard code generation? NP hard code generation. Definition: Code generation is a step in compiler design where high-level code is converted into efficient machine code. The goal is to use the least number of instructions and make the program run faster. However, finding the perfect, optimal, machine code for a given program is an NP-hard problem. This means there's no quick algorithm to guarantee the best solution in all cases, especially for large programs. Why it's NP-hard? The compiler has to decide how to assign registers, arrange instructions, and minimize memory usage. The number of possibilities grows exponentially with program size. Example: when compiling a large program, deciding the best order of instructions to use fewer CPU registers is like solving a complex puzzle. It's very hard to find the absolute best, so compilers use heuristics, smart guesses. Memory tip: think of NP-hard code generation as packing your suitcase perfectly for a long trip, possible but takes too long to get perfect, so you settle for good enough. Next important short question is: 5. List any two simplified NP-hard problems. Two simplified NP-hard problems. 1. Traveling salesperson problem, TSP. A person needs to visit N cities, each only once, and return to the starting city with the shortest total distance. Real-life use: delivery companies like Amazon, Swiggy plan routes for drivers. Hard part: as the number of cities grows, the number of possible routes grows exponentially, making it very hard to find the absolute best route quickly. 2. Knapsack problem. We have a bag, knapsack, with limited capacity and items with different weights and values. The goal is to choose items to maximize total value without exceeding the weight limit. Real-life use: airlines deciding which cargo to load for maximum profit or gamers managing inventory. Hard part: choosing the best combination of items is slow for large inputs. Memory tip: think of NP-hard problems as huge puzzles. TSP is equal to best trip plan. Knapsack is equal to best packing plan. Next unit 5. Top 5 long questions. First important long question is: explain NP, NP-complete, and NP-hard problems with examples. NP, NP-complete, and NP-hard problems. 1. NP, non-deterministic polynomial time problems. These are problems that are hard to solve quickly, but if someone gives you a solution, you can verify it quickly in polynomial time. Example: Sudoku. Solving a large Sudoku takes time, but if you are given a filled grid, checking if it's correct is easy. Key idea: hard to solve, easy to check. 2. NP-complete problems. These are the toughest problems in NP. If you find a quick, polynomial time solution for one NP-complete problem, you can solve all NP problems quickly. Example: traveling salesperson problem, TSP. Find the shortest route to visit all cities once and return home. Key idea: they are the benchmark hard problems of NP. 3. NP-hard problems. These are problems that are at least as hard as NP-complete problems or even harder. They may not be verifiable in polynomial time. Example: halting problem. Deciding whether a program will stop running is impossible to solve for all cases. Key idea: harder than NP-complete, may not even be checkable easily. Relationship, easy analogy. Think of puzzles. NP is equal to you can check if a completed puzzle is correct quickly. NP-complete is equal to the hardest puzzle among all checkable puzzles. NP-hard is equal to puzzles even harder than NP-complete, some may not even be fully checkable. Quick memory trick. NP is equal to easy to verify. NP complete is equal to hardest in NP, solve one, solve all. NP hard is equal to even harder or uncheckable. Next important long question is: 2. State and explain Cook's theorem in detail. Why is it important? Cook's theorem. Statement. Cook's theorem states that the Boolean satisfiability problem, SAT, is NP complete. This means 1. SAT is in NP. Its solutions can be verified quickly. 2. Every problem in NP can be reduced to SAT in polynomial time. So, SAT is the first NP complete problem ever proved. Explanation in simple words. Before Cook's theorem, 1971, there was no formal proof that NP complete problems even existed. Stephen Cook showed that SAT is NP complete. This was groundbreaking because if you solve SAT quickly, all NP problems can also be solved quickly. SAT asks: given a Boolean expression, with and or not, is there a way to assign true-false to variables to make it true? For example, for x, y, x, z. If x is equal to true, y is equal to false, z is equal to true, the formula becomes true. Cook showed how to convert any NP problem into SAT in polynomial time. Importance. 1. Foundation of NP completeness. Cook's theorem created the entire theory of NP complete problems. 2. Benchmark. Proving a problem is NP complete is now done by reducing it from SAT. 3. Real-world impact. Problems like scheduling, optimization, and route planning are NP complete. So Cook's theorem tells us why they're so hard. Easy analogy. Think of SAT as the mother of all puzzles. Cook proved that solving SAT is like solving every puzzle in NP. If you crack SAT quickly, you crack all NP problems. Quick memory trick. Cook's theorem is equal to SAT is NP complete. All NP problems can be turned into SAT. Next important long question is: 3. Describe the procedure to prove that a problem is NP complete. Procedure to prove a problem is NP complete. To prove a problem is NP complete, we need to show two things. Step 1. Show the problem is in NP. We prove that if someone gives us a solution, we can verify it quickly in polynomial time. Example, for a Sudoku puzzle, given a filled grid, we can check if it's correct in polynomial time. Step 2. Use polynomial time reduction. We reduce a known NP complete problem to the new problem in polynomial time. This means if we solve the new problem quickly, we can also solve the known NP complete problem quickly. Reduction shows the new problem is at least as hard as NP complete problems. Formal steps. 1. Pick a known NP complete problem, P1, like SAT. 2. Convert P1 into your problem, P2, using a polynomial time algorithm. 3. If solving P2 also solves P1 quickly, P2 is NP hard. 4. Since P2 is already in NP, step 1, P2 is NP complete. Example. To prove graph coloring is NP complete. 1. Show verifying a coloring is easy. Graph coloring is in NP. 2. Reduce 3 SAT, NP complete, to graph coloring. 3. Since graph coloring is as hard as 3 SAT, it's NP complete. Easy analogy. Think of proving someone is as strong as a champion. You. 1. Check they can lift weights, verify easily. 2. Show the champion's challenge can be turned into theirs. If they succeed, they're as strong as the champion, NP complete. Quick memory trick. In NP, easy to check solution. Reduce, turn a known NP complete problem into this one. if both true problem is NP complete. Next important long question is 4. Explain NP hard graph problems with suitable examples. NP hard graph problems. Definition. NP hard graph problems are problems related to graphs that are at least as hard as NP complete problems. They may or may not be in NP, but finding an exact solution is extremely difficult for large inputs. Common examples. 1. Traveling salesperson problem, TSP. Problem, find the shortest route to visit all cities exactly once and return to the starting city. Graph form, cities is equal to vertices, roads is equal to edges with distances. Why NP hard, number of possible routes is equal to factorial of cities, n grows very fast. Exact solution is impractical for large graphs. 2. Hamiltonian cycle problem. Problem, find a cycle in a graph that visits each vertex exactly once and returns to the starting vertex. Graph form, vertices is equal to points, edges is equal to connections between points. Why NP hard? Checking all possible cycles takes exponentially long as the graph grows. 3. Graph coloring problem with minimum colors. Problem, assign colors to vertices so that no two adjacent vertices have the same color using the fewest colors. Graph form, vertices is equal to tasks, edges is equal to conflicts. Why NP hard? As vertices increase, number of coloring combinations grows exponentially. How they are solved? Exact solutions are practically impossible for large graphs. We use heuristics or approximation algorithms to get near-optimal solutions quickly. Real-life applications include delivery route planning, scheduling tasks, frequency assignment in networks, and map coloring. Easy analogy. Think of NP hard graph problems as super difficult puzzles. Cities to visit is equal to puzzle pieces. Connections edges is equal to rules. Solving exactly is equal to arranging all pieces perfectly. For large puzzles, you usually go for good enough solutions instead of perfect ones. Memory trick. NP hard graph problems is equal to huge graph puzzles. Examples is equal to TSP, Hamiltonian cycle, graph coloring. Next important long question is 5. Write a detailed note on NP hard scheduling problems with an example. NP hard scheduling problems. Definition. Scheduling problems involve assigning tasks to resources, like machines, workers, or time slots, to achieve a goal, such as minimizing total completion time or meeting deadlines. When these problems become extremely complex, they are called NP hard scheduling problems. Why they are NP hard? The number of possible schedules grows exponentially with the number of tasks and resources. Finding the perfect schedule is practically impossible for large instances. Exact solutions take too long, so heuristics or approximation methods are often used. Example, job shop scheduling. Problem, a factory has several machines and jobs. Each job has a sequence of operations that must be processed on specific machines. The goal is to finish all jobs as soon as possible. Graphical view. Jobs is equal to vertices. Edges is equal to sequence constraints, operation order. Machines is equal to resources to allocate. Why NP hard? With 5 jobs and 3 machines, there are many ways to assign operations. The total combinations increase exponentially with more jobs or machines. Step-by-step idea. 1. List all jobs and their operation sequences. 2. Assign operations to machines respecting constraints. 3. Try to minimize total completion time, make span. 4. If a conflict occurs, two operations want the same machine, backtrack or adjust order. Real-life use. Factories scheduling production lines. Airlines scheduling flights and crew. Cloud computing assigning tasks to servers. Easy analogy. Think of NP hard scheduling like organizing a big wedding. Many events, tasks. Limited halls or rooms, resources. Some events must happen before others, constraints. Finding the perfect schedule is very hard. You settle for a good schedule. Memory trick. NP hard scheduling is equal to too many tasks plus too few resources is equal to super tough puzzle.